Alright, so we started recording, and before we begin, I wish you all a very good morning. Welcome to this second day of the faculty development program. So, I'm going to switch off the video now in view of bandwidth. And before we start with the second session, for me at least, I will just quickly discuss the point about using a 3D printer that I mentioned yesterday in the last session. So, alright, so 3D printing, there are two kinds of 3D printing. The first kind is the hobbyist 3D printing that you know, and that is called as the additive 3D printing. And additive means that there is a nozzle through which filament comes out, and this filament is getting deposited layer upon layer. Okay, when it gets deposited layer over layer, you get the final product. Now, this filament can be made of ABS, which is also a polymer. And now the important fact is ABS is soluble in acetone. So what you can do is you can 3D print a very complicated section, something like this. Now, this acts as the mold. This acts as the mold. Now, when you pour PDMS throughout this, so suppose now this ABS is completely embedded inside PDMS. Supposing that this ABS filament is completely embedded inside PDMS. Now, you can simply place this cured PDMS with the ABS into a, a petri dish which contains acetone. So the acetone will eat away the ABS filament, but it will not eat away the PDMS. It will not away. It will not eat away the PDMS polymer. So with the help of this, you will actually get the cavity which exactly resembles whatever the shape of ABS was. So this is direct. So with the help of this 3D printing, you are directly able to print the mold. So the drawback of this is the ABS filaments that you can print, they are going to be not so uh, thin compared to the other molds. One more. Whereas there is the second type of 3D printing. It's called as a DLP printing. So in DLP printing, what happens is, if I look at the side view of the printer, there is a screen and there is a vat of polymer. So it is a vat of UV sensitive polymer. And below this, there are UV LEDs. So these UV LEDs are always on while this vat contains a liquid. Now this screen has a resolution of 4K. It's a very high pixel density screen, and it offers a resolution of 35 microns in the X and Y direction. So the X and Y directions are in the paper. So this is the X and Y is into the plane. So in the plane of the screen, you get a resolution of 35 microns. So if I look at the pattern from the top, I will simply see a screen, and there are a lot of pixels. So 4K has a lot of pixel density. So now what happens is this display is connected to the processor, and suppose you want to make a small object like this. So if you look at this particular layer, if I look at the top view of this particular layer, it would be something like this. This is the material that you would get if you slice this particular object. So if I were to create this layer using this UV sensitive polymeric liquid and UV LED, I must allow light to only pass through this annulus. So the screen, the processor will tell the screen that you switch on only those pixels like this. So the screen will only switch on the pixels in the annulus. When the pixels are switched on, the UV light is able to pass through these pixels. UV light is being blocked by these regions, while UV light is only able to pass through this annulus. All right. So this, when UV light passes through this annulus, so UV light goes like this, and it therefore hardens a layer like this in the vat. Okay, there will be a layer formed like this, which will be exactly this annulus. So this is how you can also create uh, prints with very high resolution with the help of a DLP printer. And DLP printer are now becoming more and more uh, commonplace in consumer electronics as well. And in both the cases, the molds can be simply made using CAD. You can use any CAD software. There are various CAD softwares. FreeCAD is a very free alternative. OpenCAD is also a very it's also a free alternative to many of the commercial ones. The commercial ones are SolidWorks, then Fusion 360, and so on. So these are the commercial ones, these are free ones, but you can get your job done in any of those. And apart from this, there is also one very simple technique, but you will not get a lot of control. You simply put a needle, you can put the needle in between a frame. You can put the needle on a frame, so it's suspended between these two walls, and you can pour PDMS over here. You can pour PDMS. So after you are done curing the PDMS, you will have a block of PDMS which has a needle passing through it. And if you treat the needle a priori with some silicone spray, okay, you spray the needle with silicone spray, then you can easily draw this needle out. You can pull out this needle. So when you pull out this needle, you will be left with a block of PDMS with a cavity, and that cavity was exactly where that needle was residing. And now simply you can put the stainless steel connectors like this, and you can connect this to a tube, and you can connect this to a tube. Therefore you have a very simple microchannel. So the thinner needle you use, the thinner will be the microchannel. So there are various ways of getting the job done. One need not be always restricted by photolithography. Okay, so with this we stop this particular manufacturing aspect, and we will now move on to the other aspects that we are going to cover. So today's session will be on flow through microfluidic devices. So let me share screen. So let me share screen. So do let me know if my screen is visible.
Yeah, sir, it's visible.
All right. So day 2, session 1, flow through microfluidic channels. And so let me just quickly ask you what kind of, so everyone is from a very different background. So how many of you feel that the mathematics background is not that strong in your case? If that is the case, we can proceed in a more physically, in a way that makes more physical sense and not focus so much on the mathematics of it. So there is nothing wrong in that also, because I know that many of you come from a very broad background. Some come from biology, some come from IT, some come from electronics. So in that case, we will do that. We will proceed in a very in a way which makes physical sense. And I will just give a broad overview of the mathematics involved so that it doesn't become overwhelming for some of you. All right. So what are okay. So far what we have done is we have found a way to fabricate channels. So after we fabricate channels, the channels will look either something like this, or it may look something like this, or there can be a variety of grooves. So this is a rectangular groove. This is a triangular groove. And we know that these grooves can be formed due to the nature of the underlying substrate. And then you bond it from the top with glass. This glass extends. So if I look at the thing from this side, this is the rectangular groove and there is a glass layer on the top. Similarly, there is a triangular groove and there is a glass on the top. You bond the glass. And now when you have a flow, the flow will actually take place through these conduits, through this particular cavities that we have created using fabrication. Okay. So the governing equation, we will not discuss so much about the governing equation per se, but we will discuss first about the logic behind the governing equation. So the governing equations are primarily two, and as we move on, we will introduce various other concepts to this. But the governing equation essentially involves mass conservation and momentum conservation. So the mass conservation equation states that if I were to consider a small imaginary volume, if I were to imagine this imaginary volume in the flow, the flow is going through the volume. If I just draw the volume separately, I have this volume. So the conservation of mass will tell me that under steady state, whatever mass is coming in, I will tell what this m dot is going to be equal to the mass going out of the system. So m dot is the mass flux. And what do we mean by flux? It is the amount of mass that is crossing a certain boundary. So let us quickly look at what this flux is. So if I consider this face A, B, C, D, if I were to only draw this face A, B, C, D. So now flow is into the paper, so I can draw it like this. I can draw it like this. Or if I look at the isometric view, flow is going like this. So if someone were to say, what is the flux of velocity? So let us write down the flux of a certain, or rather of a velocity. So the flux will be equal to the velocity multiplied by the projected area. So if the area is orthogonal to the velocity, so over here in this particular case, the velocity is orthogonal to the area shape, to ABCD. Then it will be simply velocity times the area of the entire object. And this is simply the formula for the flux. Now let us see what this flux of velocity actually can be interpreted as. What is the interpretation of the flux of velocity? So let us say we have this same area A, B, C, D, and we say that there is some velocity V over here. Now after a time delta t, after some time delta t, if this area were to move along with the same velocity, so the area will not change. So let me grab this. The area is not gonna change, but A will now go to A prime, B will now go to B prime, D will now go to D prime, and C will now go to C prime. And they are moving because we imagine that this area is going to move with this velocity. So after a time t, after a time rather delta t, what is the distance moved by each of the points? Anyone? What is the distance moved by the area?
V times delta T.
Very good. So it will be V times delta t. So this distance is going to be velocity times delta t. It's a very simple thing that the length, the distance is equal to speed times the time difference. All right. So now what is the volume swept by the area? So essentially we are asking what is the volume between A, B, C, D and A prime, B prime, C prime, D prime. What is the volume? So we know that this length is equal to V delta T. So what will be the volume? Anyone?
A times V delta T.
So it will be the area times V delta T. Very good. So the volume swept in time delta T is equal to area times velocity times delta T. Okay, so this is the expression for the volume swept in time delta T. So if I call this delta Q, because it will depend on delta T as well. If delta T is very large, then delta Q will be very large. So delta Q over delta T is going to be area times the velocity. So this is the volume swept per unit time. If I take the limit delta T goes to 0, this will be equal to dq dt. So the area times velocity has the interpretation of the volume swept per unit time. It is the rate of volume being swept. So it is also called as the volumetric flux. Okay, it is the volume swept per unit time. By the velocity. Okay. So now if someone says that what is the mass swept? What is the mass flux? Someone's mic is on. All right. So if we look at this expression, someone's mic is on. So the mass flux will be equal to, if I look at this expression, so what is mass? It is density times the volume. So I will simply multiply it by rho, which is the density of the fluid. And so similarly, if I say the mass flux, it is equal to the mass swept per unit time.
இந்த செமஸ்டர்ல முடிக்கணும்.
Pardon me?
I don't have opinion. My requirement is technology should be completed this semester. वो पहले था सब plan. That is what my plan is. Now you want to change, it is you who wants to change.
Yeah, Mohammed Yusuf Kafir. You need to mute your mic. I know there are some issues with your semester teaching load, but that happens. All right. So now we know that the expression for the mass flow rate is rho times A times B. Okay, but see, these are big areas, meaning this we have assumed that the velocity throughout this area is constant. Okay, we are assuming that the velocity throughout this area is constant, and so we can simply say that Q is equal to V times A. Let us consider a different case where you have a circular cross section, and if I were to look at the isometric view of this circular cross section, there can be a case that the velocity, if I were to draw the velocity as vectors, has this particular profile. So this is the tube, meaning that the velocity at the center of the circle, okay, is highest, while the velocity at near the tube surface is zero. We can have a situation like this. So in this case, how do we figure out the flux of velocity? If the velocity is varying over the area, see, when the velocity is constant over the area, you simply multiply it like this. In this, we assume velocity is constant over the area. So when the velocity is not constant over the area, the flux would be an integration of the velocity over all the differential areas. What does this expression mean? That I can construct this area in small parts. So there are multiple ways I can do it. I can consider many such small squares and cover the entire area. So then, in order to find out the flux through this small area, it will be, so if the area is dA, so the flux through this will be V times dA of this area. Then the flux through this will be again V times dA. So then I have to sum over all the V times dA, and I have to sum over all such small areas. And when the dAs are very small, we know that the summation is equivalent to an integration. So that is why it becomes an integration. But in certain cases, the problem offers us certain symmetry. So we can exploit those symmetries, and instead we can choose a differential area like this. So this is a differential area. So now this area is dA. So let me ask you, what is the differential area? What is the differential area shown in the figure? What is the differential area shown in the figure? It's a circle, and let's say that the radius of this circle is capital R, and this ring, this annulus that we have, has some radius small r. So how do you find the differential area?
2 pi r into dr.
So it will be 2 pi r into dr. And we can verify that this is correct. So this is dA. So now the area, total area of the circle will be integral 2 pi r into dr, where r varies from 0 to capital R. So this will be 2 pi r square over 2. So this cancels out and it becomes pi r square. So this is the correct answer. All right. So now what we have over here is the velocity is now a function of the radius. This is r. This surface is r equal to capital R, and this center line is r equal to 0. So it means that when we want to find out this integration, it will be integral of the velocity, which is actually a function of r, times the dA, which is equal to 2 pi times r dr. So this will now be the expression for the volumetric flux. And we cannot evaluate this at this moment as we do not have any expression for the velocity as a function of r. Let us imagine a very simple situation where the velocity varies radially. Let us say that the velocity is zero, or rather velocity is zero over here and it has a maximum over here. So what can be a profile, or even something like this we can imagine. Let us write down the profile. So the profile will be uh, capital R square minus R square. So this can be a tentative profile because we know that when r equal to 0, the velocity becomes equal to r square, and at r equal to plus minus r, or in this case it will not be plus minus, it will be simply r, the velocity is 0. So we have the 0 velocity at the surface and the maximum velocity at the center line. So let us now perform this integration for this particular case. So the flux q will be integral r square minus r square, that is the expression for v, times 2 pi r. Yeah. So 2 pi can come out of the integration. So it is 2 pi integration. So now we multiply this r to both the terms. It will be r square times r minus r cube. And this will be dr. And r goes from 0 to capital R. So this will be 2 pi. So what will be this? So let us do the integration first. So it will be r square over 2. The limits will be 0 to r minus r to the power 4 over 4. The limits will be 0 to r. So this is 2 pi. So this will be r to the power 4 over 2 minus r to the power 4 over 4. So finally you have 2 pi r to the power 4 over 4. And this is pi r to the power 4 over 2. And the reason why I have focused on finding out the flux of the velocity is because we will be needing expressions like this in our study of pressure driven flows. So just make sure you understand how to find out the flux of a velocity. Well, I just want to tell all of you a small caveat about all of this. I said that the flux is V dA and the integration of this over the area. But this expression is not entirely true. There is something which I have hidden in this expression. Okay. So let me just quickly tell you about what is hidden in this expression, and hopefully you will be able to appreciate that yes, this is a fine aspect, but in majority of the cases it may not be worrisome for us. What had I said about the area sweeping? So the area is like this, the velocity was something like this, and we imagine that the area is moving with the velocity, and therefore it sweeps a volume. It is able to sweep a certain volume. When will the area not sweep a volume? When will the area not sweep a volume? Anyone?
When it is perpendicular.
All right. So that is the correct answer. So when the area is like this, but you are now moving the area along in the plane of the area. Okay. When you are moving the so imagine you take a piece of, let me switch on my video, I'll quickly show it. I'll show the demonstration. I have a small coaster in front of me. Let me know if you can see me. Can you see me?
Yes, sir.
I need to be spotlighted or what? All right. So you have an area. Let me turn off blur. How do you do that? Okay. Yeah. So you have an area like this. Now you take this area and you are sweeping it like this. You are sweeping the area. So when you sweep this area, you will get a certain cylinder. Okay. And the and the volume of the cylinder will be the distance swept by the area times the area of the coaster itself. Okay, you are sweeping a volume, you are creating a cylinder. But now if I take this volume, if I take this area and I move it in the plane of the area, I am only able to sweep a volume equal to this thickness. But this coaster, where I keep my T, is a very is an idealization is not an idealization of what an area is supposed to be. An area is supposed to be having no dimensions in the third direction, meaning the sheet of paper can be my area. So the sheet of paper actually has no volume. And now when this sweeps in this direction, it is actually cutting no amount of volume. It will sweep zero. So if I were to sweep this, what kind of object will be formed? If I take this area and I sweep it towards you, what will be the shape that will be formed?
Cuboidal.
It will be a rectangular parallelepiped. All right. So I hope it is clear that you need to sweep. You need to sweep the area appropriately. You cannot just sweep it randomly. So the mathematical way of describing this fact that the direction of sweeping is important is achieved by defining what we call as the area normal of a vector. The area normal of a of an area. So this ABCD has an area normal like this, meaning it is a vector. It is a vector which does not lie in the plane of ABCD. Okay, it is a vector orthogonal to the area. So let us imagine a cylinder. Let us imagine a cylinder. How does the area vector look like for the cap? How does the area vector look like for this particular cap?
Perpendicular outward.
Will it be like this?
Yes.
Or will it be like this? Or will it be like
First one. Going up.
which one?
Going
One.
up.
Okay, it will be going up. So that is the correct answer. The area vector will actually be going up. Now the question is, pardon me, what will be the area normal for this curved surface now? Now you have a curved surface. What will be the area vector for this?
That will go right side and that will be perpendicular on that line.
So let me draw.
Radially outward.
It will always be radially outward. So if I draw the top view of this, so it will be like a circle. The top view will be a circle. So everywhere the area normal will be radially outward. So it is changing with direction. Okay. All right. So far we have understood how to take a flux of the things, and I hope things are not too complicated for you at this moment, for anyone. One moment. And the thing is, the development of fluid mechanics was primarily done by applied mathematicians, and so the the fact that mathematics enters over here is not to complicate things, but it is to actually make things quite simple. But without knowing the language of mathematics, or without knowing the notation or the purpose, things start becoming very complicated. But I can assure you that the description of the fluid mechanics has to be done through some idealizations, through some notations. Otherwise, it will not be easy to define what kind of flow is going on. Okay. So, without further ado, let me tell you about the conservation of momentum. So, that was the conservation of mass. Mass coming in will be the mass going out. All right. So, now conservation of momentum. Imagine once again you have an imaginary, let me draw it slightly bigger. You have an imaginary cube like this, and this cuboid is filled with the liquid. So what does the conservation of momentum tell us? That it's Newton's law basically, that the rate of change of momentum will be equal to summation of all the forces acting on it, right? So now what kind of forces can act on this? There are two kinds of forces that can act on this. One is on this volume. On the volume, we can have surface forces or we can have body forces. Okay. So body forces, for example, gravity. Gravity, so the mass of an object times the gravity, that is like the force which depends on the mass of the object. But surface force is something which is dependent only on the area of the object. So the mass depends on the volume. So body force depends on the volume, but surface forces, they only depend on the surface. Now let us say that there is some pressure over here, P1, and there is some pressure over here, P2. So in the x direction, if I declare this as the x direction, and if the area here is A, and if the area here is also A, so what do you think will be the force acting in the x direction due to pressure?
P1 minus P2.
The total force in the x direction will be P1 times A minus P2 times A, right? And this will be P1 minus P2 times A. Now, if this is the x direction, if I say that this is the dx, if I say that this distance is dx, meaning I say that the distance is quite small, it is not a very large cube, it is a differential element. I say that this is a differential element and this distance is dx. Now the next question that we will pose is there some way of expressing P2 in terms of P1? Is there a way of expressing P2 in terms of
By
P1.
using Taylor series.
Yes, that is the correct answer, and it is by the means of Taylor series. So, I mean, I don't know who answered. It says, did Rakesh answer? But I'd like to know from the others whether you are aware of what a Taylor series is.
Yes, sir.
So Ravikant knows. Anyone who is not aware, we will just write down the formula and we will tell the interpretation. Even if you do not, if you have not seen it or if you have forgotten, we will try to.
You can Peter sir if you write because many might not be knowing.
They might have been out of touch for a while, but okay. So what it means is we will use a Taylor series, and it means that if you have a function at a certain point in the domain, let's say it's only a function of x. So let's say that at this point the function is f of x. I can write down an approximation of the value of the function at a distance delta x from the point under consideration. So this is the point under consideration. So I can write down an approximate expression for the function at a distance dx. So that will be f at x plus dx or delta x will be f of x plus df dx delta x plus d2f dx2 1 over 2 factorial delta x square and so on. And what it simply means is the value of the function at x plus delta x can be written in terms of the value of the function at x plus the slope of the function times delta x plus the curvature of the function times delta x square and so on. Okay. So if we were to keep only the first two terms on the right hand side, then we have f x plus delta x is equal to f of x plus df dx delta x. And this might be a good place to actually explain what the Taylor series is. If I were to rearrange these terms, if I rearrange these terms, what will I have? Df dx is equal to f x plus delta x minus fx over delta x. Okay, if I rearrange, then I get this approximation for the slope. Okay, so with this in mind, I can write this as p1 minus p1 plus dp dx delta x only as the first approximation times a. So the due to pressure, the force is equal to p1. So this p1 and this p1 they cancel out, and we are left with minus dp dx delta x times a. And this will be equal to, if I write down that the rate of change of momentum is this, then this will be d dt of mass times the velocity in the u direction, because the momentum has three components, because it's basically mass times the velocity, and velocity has three components. So we said that the velocity has three components. So the x component of velocity is called as u, the y component of velocity is called as v, and the z component of velocity is called as w. This is classic notation that is used throughout fluid mechanics. So the momentum in the x direction will be only m times u. And so ddt of, so what is mass? It is density times the volume. Now what is the volume? What is the volume of this? What is the volume of this cuboid? It is going to be area times delta x. Do you agree? The volume is going to be area times delta x, right? Am I audible?
Yes, sir.
Hello? Yeah, okay. I think there is a lag between transmission. So on the left hand side, we have minus dp dx times delta x times a. So this delta x a, this business cancels out. So we have ddt of rho times u is equal to minus dp dx. What does it mean? That in order to have a positive change of momentum in the x direction, in order to have a positive change of momentum in the x direction, what should be the sign of, what should be the sign of dp dx? What should be the sign of dp dx? If the left hand side is supposed to be negative, if the left hand side is supposed to be positive, then what should be sign of dp dx?
So if flow is happening from left to right, the pressure should be higher on left side. So
Yes,
dp by dx.
that is correct. But here, I mean, let's just look at this expression for now. So the dp dx has to be negative. See, on the right hand side, you have minus 1 times dp dx. So if dp dx is negative, then negative and this negative they multiply and this entire term becomes positive. So we say that in order to drive a flow, the pressure gradient must be negative. In order to drive a flow, the pressure gradient must be negative. And this is exactly what someone just mentioned right now. So the if the flow has to go from left to right, the flow has to be like this. Intuition does say that the pressure over here, if I call it P1, I call this P2. So P1 has to be greater than P2. Otherwise, how will it push the fluid? Okay. So P1 greater than P2 for X1 less than X2, because this is X1, this is X2. As X is increasing, the pressure is reducing. As X increases, P reduces. Meaning P2 minus P1 over X2 minus X1 is negative. And hence, this kind of pressure gradient is called as a negative pressure gradient. Okay, so you must remember this, that in order to drive a flow, the pressure gradient has to be negative. One cannot have a positive pressure gradient and still drive the flow in that direction. All right, so then we come to the next idea, that of viscosity. So now we now know that pressure can drive a flow, but there must be some mechanism by which the energy is being lost. Otherwise, if no energy were to be lost, I can just give a small push to the fluid, it will go forever. What happens if you take a big bucket, fill it with water. If you take a small stick and move the stick, you will see that the liquid will have some swirling action. After a few seconds, the swirling will completely die down. Whatever motion was set by the action of the rod it dies down. What is the reason the action or the motion dies down? The motion of the water, this swirling, whatever goes on, that will eventually die down and everything will become static. Why? What could be the mechanism for this?
Viscosity.
Yes, the answer is viscosity. So viscosity is the only mechanism in fluid flow that is responsible for dissipating energy in the flow. One moment. So viscosity is the only mechanism by which we are able to have dissipation in the flow. So let's quickly discuss some of the ramifications when a flow has viscosity and when the flow does not have viscosity. Well, what I wrote was a very elaborate way of saying an inviscid flow. This is also known as an inviscid flow. Now look, it's very simple. Let us look at a thought experiment. And I'm discussing these ideas because eventually they will be used in declaring what kind of boundary conditions you have and all these things. So it is prudent to discuss this. Imagine you have the plate like this. And you have some velocity profile, some uniform velocity arriving over it. And this uniform velocity eventually reaches the edge of this plate. So immediately next to the plate, the velocity, the fluid molecule that is actually being flown, it will see that what will be the fluid molecule seeing? It will see that here there is zero velocity and here there is some velocity. So the velocity of this molecule will be the average between this velocity and this velocity. So it will be, so the molecule which is directly at the wall will stick at the wall, but the molecule intermediate will see that there is some loss of momentum because of the stationary wall. So this velocity will be lower. Similarly, this velocity, this molecule will see a lower velocity and somewhat higher velocity. Similarly, this molecule will see that, okay, this still has some momentum, but it is lower than the momentum of this. So this will have some intermediate momentum. So the layers would organize themselves in the form of a velocity profile. But does this happen instantaneously? And the answer is no. It requires time for this signal to propagate throughout the fluids that the wall is stationary. So initially only the first layer will be able to feel the effect of the wall. So that will have a very small velocity. But the other layers are almost oblivious to the fact that there is some kind of obstruction. So the profile will actually look like this. Everywhere it will be the same velocity as the incoming velocity except near the wall. Now that this velocity has reduced, at the next axial location, the molecules will see, wait, this is at a lower velocity, so I must readjust my velocity. So the velocity profile will become something like this. Now more layers have been affected by the influence of the wall, but away from the wall it is all constant velocity. Okay, so if I were to connect the points where where the fluid layer is merging with the uniform velocity, if I call it u infinity, there will be some point after which the effect of the wall will not be felt. So if I connect this, so this particular layer is called as the boundary layer. And the boundary layer is formed solely because of the presence of viscosity. If viscosity is not there, if viscosity is not there, then there is no reason for the molecule to actually stop. It is like playing with a marble. You know those glass marbles? When you play with a glass marble on, say, very polished and hard surface of marble, what do you call this? Kancha. I call it kancha. What do you call a glass marble?
Kancha only.
Kancha only. Okay. So when you play kancha on a hard marble surface, you will see that if you give some momentum to the glass marble, it will keep on moving, right? It will, it will not even look to stop anywhere. It will keep on moving, right? Have you experienced this? Versus you play marble on mud. What is the difference between these two scenarios? Anyone?
Surface.
No, surface, but what is the physical manifestation
Friction is
of this?
higher. Frictional force.
The friction is changing. So viscosity is equivalent to the friction between the fluid molecule and the surface. Very good. That is the exact analogy I was looking for. Viscosity is the friction between the fluid molecule and the wall surface. In fact, viscosity is also the friction between fluid molecules and fluid molecules also. Now, with the above thought experiment that I just mentioned, okay, this above thought experiment is like you have a bunch of marbles going over a flat boundary. So if this is mud, then this velocity will be lower. Then because this is lower and because the marbles are interacting, this velocity will be also lower. So this will be, the marble at the wall will be zero velocity. This will have some velocity. This will have some higher velocity. This will have even a higher velocity. And afterwards, it will all move with uniform velocity. But when there is no friction, then what kind of velocity do you expect? When you have an incoming flow with u infinity, what kind of velocity do you expect when there is no viscosity?
U infinity.
It will be uniform everywhere.
Yes, sir.
Is it clear to everyone? So viscous flows have have a property which is called as the no slip boundary condition. And what this means is, at the walls, it need not be a flat wall, it can be a curved wall as well. The velocity tangential to the wall, or rather the relative velocity tangential to the wall, will be equal to what? Zero. Okay. The velocity relative to the wall will be zero. So let us look at one more example. I know it's winter time, so many of you may not be using a ceiling fan, but for those of you who are using a ceiling fan, you will see that when the ceiling fan starts, right, immediately you will not get air. You will get it after 1 second, because the air is the blades are transferring momentum to the air, so that all those layers of air will eventually transfer momentum to you. In fact, because of viscosity, a person standing far from the fan will not be able to feel the effect of the fan, because by that time the velocities have died down. So viscosity will dissipate all the energy. Okay. So flows in microchannels are dominated by viscosity. And this fact is quantified by the Reynolds number. So it is not apostrophe S, it is not this, it is Reynolds number. The name of the person was Osborne Reynolds, and he quantified a number which looks like this, where rho is the density, okay. So it establishes how dominant inertia is compared to viscosity. If inertia is very much dominant, then you will have high Reynolds numbers. So high Reynolds numbers, so we call it RE. So high Reynolds number flows versus Reynolds number flows. So high Reynolds number flows, you will have atmospheric flows, flows in big pipes, flow over car, all these things flow over aeroplane, because they are moving with a high velocity. They will have a high Reynolds number, and even the lengths are very large. But in microchannels, the lengths are small, the velocities are small, right? So let us look at an example. Suppose you have a flow in a very fine tube. So the tube is 100 micron in diameter, and the velocity is 1 millimeter per second. So then let us calculate the Reynolds number for water. So what is the density of water? 10 to the power 3 kg per meter cubed times the velocity. So 1 millimeter per second, if I convert into meter per second, it will be how much? 1 millimeter per second is how many meters per second?
Ten to the power minus three.
It is 10 to the power minus 3 meter per second. What is the length? So length is 100 micrometer. So how many meters is this? 100 micrometer. It is 100 times 10 to the power minus 6 meter, right? So this is 10 to the power minus 4 meter. This divided by the viscosity. So what is the viscosity of water? It is close to 10 to the power minus 3 Pascal second. So this cancels out. So this becomes 10 to the power minus 1. Reynolds number is 0.1. So it is small. Okay. Similarly, for flows of say sperm cells or a sperm, the sperm diameter is maybe 20 micrometer or 10 micrometer or 3 micrometer, something like that. So it is tens of micrometer. So let's say it is 10 micrometer for convenience. Now this sperm is moving in a fluid which is not exactly water, but as a first approximation you can consider it to be water. So what is the Reynolds number for this kind of flow? So the density of water is again 10 to the power 3. The velocity, so this velocity will now be tens of micrometer per second, so 10 to the power minus 5 times the length. So the length scale is 10 micrometer, so again 10 to the power minus 5, and the viscosity is 10 to the power minus 3. So what is this? So this becomes 10 to the power 6, this 10 to the power minus 10, so this is 10 to the power minus 4. So again this is very low Reynolds number. What is the Reynolds number of a plane in motion? Aeroplane. So the span of the aeroplane is tens of meters, so let's say it's 10 meter length. The density of air is around 1, it is 1.2 kg per meter cube, but we can assume it to be 1. The viscosity of air is 10 to the power minus 6 Pascal second. Okay. So let's, and what is the velocity of a typical aeroplane? How many meters per second?
500, 600
Let's say it is
kilometers
500.
per hour.
So those many kilometers per hour, you have to convert it into meter per second. So look, we can easily estimate that using the velocity of sound. So the velocity of sound is how much in meters per second?
330.
340, right? So we know that the aeroplane cruising speed is 0.7 times the velocity of sound. So it is going to be 0.7, or it is, if even if it is not going so fast, let's say it is 100 meters per second for a rough estimate. So what is the Reynolds number for this? It is 1 times velocity 100 times the length, which is 10 over 10 to the power minus 6. So this becomes what? 10 to the power 9. So Reynolds number for flows happening over aeroplane or cars and all these things are very, very large. Okay, so we'll take a 5-minute break. But so far, what have we studied? We have studied the flux of velocity, the flux of mass. Then we have looked at how pressure is able to exert force on the fluid, and we are able to see the no-slip boundary condition and the important concept of Reynolds number. So far we have studied this. In the next part of this session, which will start after 5 minutes, we will look at the mathematics of what is known as I mean, we call it Poiseuille, but it's a French name, so it's Poiseuille flow. Poiseuille flow. So we will look at this and how we can derive
Sir,
all the important. Yeah.
Sir, one question. You have considered while deriving momentum equation, you have considered pressure only as body force, or
Yeah.
sorry, surface force,
Yeah.
but you have not considered any stresses or something so far.
Yes.
So I was curious.
No, it is correct. I have not explicitly mentioned stresses, but the stresses, the viscous stresses, are manifested through the viscosity. And keeping in mind the broad public who might have not done fluid mechanics course, so then I would have to first discuss a stress tensor and then the traction vector on an area which is oriented along any arbitrary direction. So we are going with a very qualitative understanding of the different forces that come into play without actually going into those tensorial descriptions. In my, if required, I can share with you my fluid mechanics playlist in which I have discussed them in great detail, and that was telecast on the Swayam Prabha channel. The Swayam Prabha program that went on. So in that I have discussed it in full detail, but I think given the audience, it is not prudent to discuss that in that much detail over here. So we will proceed with the Poisson flow, but we will
Yeah, sure,
not
sir. Thank you.
go into the depths of stress tensors and all that. But yes, the stress tensor does comprise of, broadly speaking, the viscous stresses, and the viscous stresses in this case, they depend on the viscosity, of course, and the deformation tensor, which depends on the gradients of velocity. So no, it is not worth our time to discuss this over here. And if required, we will discuss it whenever we encounter something where it requires some discussion, but for now we don't need that discussion. We will proceed with
Yeah, sure,
the
sir.
Poisson flow after a 5-minute break, drinks break. So I'll be right back. Let's proceed. So we've already seen that the rate of change of the momentum in the x direction is because of the pressure gradient, and we have not yet accounted for any viscous stresses, but you have to take it with a grain of salt that the viscous stresses are plus mu times, in this one dimensional case, del 2 u del y 2. So let me draw the coordinate system. And suppose the height of the channel. So we are looking at a two-dimensional channel, meaning that the cavity into the plane is infinitely long. Okay, the cavity into the plane is infinitely long. So if this is capital H, or let's say it's 2h, then this surface becomes y equal to h, and this becomes equal to y equal to minus h. So am I audible first of all?
Yes, sir.
So this particular derivative that we had written was in the classic sense. It was in the Lagrangian sense. But in fluid mechanics, we will be focused on what is called as the Eulerian description. But see, whatever I'm going to write now, it's not so critical because everything will be zero anyway. But I will write it down for completeness. So this particular derivative is the same as the Lagrangian derivative, but this is the Eulerian derivative, or this is in the Eulerian frame of reference, and this is called as a total derivative. Sometimes it is also called as the material derivative. And these concepts, one must discuss about this, about the various philosophies of it. So in the short term course, it is not exactly required, but this is what we have. Now, this is the governing equation. We also need the appropriate boundary conditions. We need the boundary conditions for the u component of velocity. Remember that the u component is the component along the x direction, whereas the v component, the v velocity, or rather the v is the component along the y direction. So what are the boundary conditions for u? We have the no slip boundary conditions. We have the no slip boundary condition for u on the walls. So this is like the, I mean, I'm calling it inlet, but there is no inlet outlet. I'll tell you why. These are the walls. So how can we mathematically describe the no slip boundary condition? We can say that u at h at plus minus h is equal to 0. Now we will say that the flow is fully developed. When we say that the flow is fully developed, it means that the flow has no longer any variation in the x direction. It means that at any x location, we will have the same velocity profile. Although my drawing is not so precise that it will look equal, but at any cross section at x equal to x1 or x equal to x2, we will say that the flow, the u component of velocity, is not dependent on x. What is the mathematical way of translating this fact?
du by dx is equal to 0.
Very good. So it will simply mean del u over del x. The partial derivative of u with respect to x is equal to 0. Okay. Now, let us look at it from another direction. So if we choose this imaginary surface as our control volume, what is happening in this imaginary surface? Some fluid is coming in, some fluid is going out. These are at two different locations. So whatever is coming in at x1 is also going out at x2. Do you agree with me? Whatever amount of flow comes in through this surface at x1 is going to be exactly the same amount of fluid going through the flow going through the surface x2. Is that okay? Does that not make
Yes, sir,
sense?
because mass is conserved. It has to be.
It has to be. And the profiles are no. So uh, mass is conserved, but that does not mean that the flow through this and this are equal. It could also mean that there is some flow leaving through these surfaces. But in this particular case, because the flow is bounded by walls, there cannot be a flow in this direction or in this direction. But anyway, because of this, what it means is throughout the channel, the v velocity, that is the velocity component in the y direction, will be 0. It is not 0 in the developing region. Okay, in the developing region, del u del x is not equal to 0. In fact, v is also not equal to 0. But in the fully developed region, del u del x is 0 and also v is going to be 0. And the more mathematically oriented way of saying is, because the flow is incompressible, if the flow is incompressible, meaning that the divergence of the velocity vector is 0. This is called as the divergence, and you might have studied this in your elementary mathematics course. So in two dimensions, this will be equal to del u del x plus del v del y. So if we have that the flow is incompressible, then del u del x plus del v del y is equal to 0. If the flow is fully developed, then what does it imply? It means del v del y equal to 0. It implies if we integrate this, v equal to constant, but there is no v velocity at the wall, meaning v velocity at the wall is equal to 0. Okay, the fluid cannot penetrate the wall. Because the fluid cannot penetrate the wall, the V velocity is 0. So this constant has to be 0. It automatically means that V is equal to 0. This is what we have shown qualitatively as well. All right. So with the help of del u del x equal to 0 and V equal to 0, let us see what happens to the left hand side of this expression. So del u del x is 0, so this entire term becomes 0. V is equal to 0, so this entire term becomes 0. And now we say that flow is steady. When we say that the flow is steady, this term also vanishes because the u is not dependent on time. So finally, we have only a balance of the right hand side terms. So we have 0 equal to this. So this can be interpreted as the pressure gradient driving the flow, and this can be interpreted as the viscosity resisting the drive of the flow. And because we know that del u del x is equal to 0, then we can simply write del u del y as du dy. And the pressure gradient driving the flow. So if you have a long channel like this, so we can actually show that del p del x is equal to delta p over delta x, and it is like a constant. If this is p1, if this is p2, right? So minus del p del x, it comes out to be p1 minus p2 over L. If L is the length of the channel, so this term is equal to this, so it becomes a constant. So this is like a constant. So let this constant be G. So we have 0 equal to G plus mu del 2 U del y2 is equal to G plus mu d2U dy. Let us solve this differential equation. So we have what? d2U dy2 is equal to minus G over mu. We can integrate this once and we can obtain du dy is equal to minus gy over mu plus constant. We can integrate it again. U is equal to minus gy square over 2 mu plus c1y plus c2. Now we must make use of the boundary conditions in order to determine the two unknown constants. So we can make use of the fact that u at y equal to h is equal to 0 and u at y equal to minus h is equal to 0. So let's do that. So if I call this 1, if I call this 2, so using 1, 0 is equal to minus g over 2 mu h square plus c1h plus c2, and using 2, we have 0 is equal to minus g over 2 mu h square minus c1h plus c2. So if we add these two equations, what do we have? 2c2 minus gh square over mu is equal to 0, which implies c2 is equal to gh square over 2 mu. And if we subtract those two equations, what will we have? We will have c1h equal to 0. 2c1h equal to 0 means c1 equal to 0. So we now have an expression for the two constants. We have u is equal to minus gy square over 2 mu plus C2. So C2 is gh square over 2 mu. So if I take gh square over 2 mu common, I will have 1 minus y square over h square. And this velocity profile, it is called as the plane Poiseuille flow profile. Okay. This particular velocity profile is called as the plane Poiseuille flow profile. Now, let us see what the volume flux through area will be. So what will be the volume flux? We know that this is the flow profile in 2 dimension. See, let us say that the width into the plane of this channel is W. Width into plane is W. So what is the differential area? What is the differential area going to be? If I draw a large rectangular slot and this width is W, it's large, it's very large. So this is the y direction and into the paper is the x direction. So what is the differential area? It will be this area of this strip, right? So what is the area of this strip? What is the area of that strip? It will it will be W into dy. So the volumetric cross flow rate will be equal to gh square over 2 mu 1 minus y square over h square. This is the velocity, and we must integrate this multiplied by W into dy. This is the width. This is not the W component of velocity. The width into the plane. So the flux per unit width will be equal to integral gh square over 2 mu 1 minus y square over h square dy. So this is all constant, so it can come out of the integration. And this integration will go from minus h to plus h. Okay. So this is gh square over 2 mu integration minus h to h 1 minus y square over h square dy. Now let me say that y bar is equal to y by h. Okay. So I will divide by h and multiply by h. So this will be gh cubed over 2 mu times integration. So now y bar will, let me just write it down, 1 minus y bar square dy bar. This h I have absorbed it over here. Okay. And at this minus h will be what? Y bar will be what over here? It will be minus 1 and y bar will be equal to 1 at y equal to h. Because when y equal to h, y bar equal to 1. When y equal to minus h, y bar equal to minus 1. This becomes gh cube over 2 mu. So what is this integration equal to? It will be 2 minus 1/3 times 2. 2 minus 2/3. 4/3. So this is 4/3 times GH cubed over 2 mu. This is 2/3 of GH cubed over mu. This is the expression for the volumetric flow rate. Let us do the I will actually give the I'll give you a handout for how to find out how to do this term derivation for a Poisson flow, which is for such a kind of flow through a circular tube, through a closed tube. I will give that as a handout so that you can take your time and have a look at it. You don't have to rush it through a derivation. Okay. Now, if someone says, what is this stress at the wall? So the shear stress at the wall will be equal to mu du dy. And this is very much similar to the Newton's law of viscosity that you might have studied in your class 11 or 12 long back. But the wall shear stress is equal to this. I mean, in this particular unidirectional flow, it is equal to this. It is not always true. There's nothing universal about this expression. But in this case, it is like this. So what is the wall shear stress? So it is mu times du dy. So if u is this, what is du dy? It is equal to gh square over 2 mu minus 2y over h square. And we will substitute y equal to h. But because the coordinate system is chosen at the center line, it will be minus of this. So we will simply take the absolute value of this. So we'll put y equal to h. So at y equal to h, du dy is equal to what? So this y will become h. So this h square they cancel out. This will be this 2 they cancel out. It will be g times h over mu. And this is mu times g times h over mu. So this mu cancels out, so it becomes equal to gh. Okay, this is how you evaluate the wall shear stress. So the wall shear stress obviously depends on the velocity gradient at the wall. Now you tell me, if you have one velocity profile like this and one velocity profile like this, both are sort of velocity profiles. So in which case will be the wall shear stress higher? In which case will be the wall shear stress higher?
Right hand side.
So the second velocity will have a higher wall shear stress because the slope of velocity is very high in the second case. Here the velocity slope is very high. It's very steep. Steep velocity gradient. And over here the velocity gradient is very mild. So the slope over here is like this. So this is a mild slope. You may very well say, but here the angle is less. But remember that the slope is du dy. Oh, sorry, I have misplaced the coordinates. This is not u and y. This is going to be the y coordinate. This is the velocity. So du dy over here is not this particular angle, it is this particular angle. Okay, so it is like delta u over delta y. So per change in y, the u value, suppose I change y by this amount. I change y by this amount, I will obtain a change in u over this amount. But for the same change in y over here, in one case u is over here, in one case u is over here. So you have a very large change in velocity for even a small change in y. So that is why this particular case the slope is very steep, here the slope is very mild. So in this particular case you will have a higher shear stress. So in the exam, I mean assessment exam, evaluation exam, there will be questions like these, very simple questions. I will share all these notes with you as well, whatever I have. Let me quickly save it. It is D2S1. Okay. I'll share this with you. I'll make a Google Drive where you can download all this. Okay, so we've come to the end of our time, the session time. Make sure one of my students will send you the evaluation link. I know it's a slightly more technical session, but I think it is needed. Alright guys, so at 11 o'clock, there will be a session by Professor Nayak from NITIE. I'm stopping recording.